lecture, we have seen the example on Fourier series expansion for even function in minus pi pi. So continuing with the same, we will take the second example again on even function. The example is like this: find Fourier series for fx is equal to x sin x in the interval minus pi pi. So here f of minus x is equal to minus x into sine of minus x, that is equal to minus x into minus sin x, that is equal to x sin x, that is equal to fx. Therefore fx is even function, and therefore a0 and an we can find, and bn will be 0. So a0 is 2 upon pi integral 0 to pi fx dx. So fx is x sin x. So x sin x dx. We use generalized by part rule to evaluate this integration and obtain 2 upon pi into bracket x into minus cos x minus 1 into minus sin x. The limits are 0 and pi. By substituting the limits and taking the difference, finally we will get a0 is equal to 2. Then an is equal to 2 upon pi integral 0 to pi fx into cos nx dx. That is, an is equal to 2 upon pi integral 0 to pi x sin x cos nx dx. Here we use the formula from trigonometry, that is 2 sin alpha cos beta is equal to sin of alpha plus beta plus sin of alpha minus beta for sin x into cos nx. So using that formula, we are getting an is equal to 2 upon 2 pi integral 0 to pi x into bracket sin of 1 plus n x plus sin of 1 minus n x dx. By multiplying x, we are getting this integration into two integrals, that is an is equal to 1 upon pi integral 0 to pi x into sin of 1 plus n x dx plus 1 upon pi integral 0 to pi x into sin of 1 minus n x dx. For both the integrations, we use our generalized by part rule, and by that rule we are having an is equal to 1 upon pi x into minus cos of 1 plus n x divided by 1 plus n minus 1 into minus sin of 1 plus n x divided by 1 plus n bracket square. The limits are 0 and pi plus 1 upon pi x into bracket x into minus cos of 1 minus n into x divided by 1 minus n minus 1 into minus sin of 1 minus n into x divided by 1 minus n bracket square. The limits are 0 and pi. After using the results again from trigonometry, what are they? Cos of pi plus theta is equal to minus cos theta. Cos of pi minus theta is equal to minus cos theta. Cos of n pi is equal to minus 1 raised to n. Cos 0 is equal to 1. Then sin of n pi is equal to 0. Sin 0 is equal to 0. Using all these results, we are getting an as 1 upon pi into minus 1 raised to n divided by 1 plus n plus 1 upon pi into minus 1 raised to n divided by 1 minus n. Pi gets cancelled for both the terms. Minus 1 raised to n is common. So an is equal to minus 1 raised to n into bracket 1 upon 1 plus n plus 1 upon 1 minus n. After simplification, this gives minus 1 raised to n into 2 upon 1 minus n square for n not equal to 1. Why n not equal to 1? Because if n is 1, 2 upon 1 minus n square becomes infinity, and therefore we impose the condition on n, that is n should not be 1. But then what is an when n is 1? That also we have to find. So for that an becomes a1 for n is 1, and a1 becomes 2 upon pi integral 0 to pi x sin x cos x. Cos x. Why cos x? Because cos nx becomes cos x when n is 1. So a1 becomes 2 upon pi integral 0 to pi x sin x cos x dx. But sin x cos x is sin 2x divided by 2, and therefore an is equal to 2 upon 2 pi integral 0 to pi x into sin 2x dx. That is equal to minus half after evaluation of the limit. Of course, Bn is 0. Therefore, required Fourier series expansion will be fx is equal to x sin x a naught by 2 plus a1 cos x plus summation an cos nx. N takes values from 2 to infinity. So putting the values of a0, a1, an, fx becomes 2 by 2 minus half cos x plus summation 2 into minus 1 raised to n divided by 1 minus n square cos nx. N takes values from 2 to infinity. By putting the values of n, that is starting value is 2, then 3, then 4, and if we expand this summation, we will finally obtain fx is equal to x sin x is equal to 1 minus half cos x minus 2 cos 2x divided by 3. 3 we can write as 1 into 3 minus 2 cos 3x divided by 2 into 4. 8 we can write as 2 into 4 minus 2 cos 4x divided by 3 into 5. 15 we write as 3 into 5 plus and so on. So this we are writing because we will get some specific pattern, and this one is our final answer for fx. The next example is find the Fourier series expansion for fx is equal to x in minus pi pi. Very simple. What we do first? First we will see whether the given function is even or odd. So for that, f of minus x is equal to minus x is equal to minus fx, and therefore our conclusion for fx is fx will be odd function. For odd function, a0 and an are 0, and therefore only remaining work is to find the value of Fourier constant Bn. So what is Bn? Bn is equal to 2 upon pi integral 0 to pi fx into sin nx dx. But what is fx? Fx is x. So 2 upon pi x into 2 upon pi integral 0 to pi x into sin nx dx. After evaluation of this limit, again using generalized by-part rule, we will get Bn is equal to 2 upon pi x into minus cos nx by n minus 1 into minus sin nx by n square. The limits are 0 and pi. That is equal to 2 upon n pi minus pi into minus 1 raised to n. That is equal to minus 2 upon n. Pi gets cancelled. Minus 2 upon n into minus 1 raised to n. Here also we are using the same results, that is cos n pi is equal to minus 1 raised to n. Cos 0 is equal to 1. Sin n pi is 0. Sin 0 is 0. And therefore, our required Fourier series becomes fx is equal to x is equal to summation bn sin nx, where n takes values from 1 to infinity, that is summation n is equal to 1 to infinity minus 2 by n minus 1 raised to n sin nx. After expanding, we will get minus 2 into bracket minus sin x by 1 plus sin 2x by 2 minus sin 3x by 3 plus and so on. So again we take minus common from the bracket, and finally we write the answer for fx as 2 into sin x by 1 minus sin 2x by 2 plus sin 3x by 3 minus and so on. Thank you. Stay at home, stay safe, and be connected. Thank you once again.